All right, so since it's already 10 plus 10, so let's get started. Good morning, everyone. So thank you so much for coming again to today's tutorial. So the midterm marks have been posted and the average grade is 65. So it's just a reminder that we have the deadline for assignment 2 tonight and the assignment 3, which will be on loop invariant code motion and register allocation, will be released the next Monday. At the meantime, if you have any issue with the midterm marking, if you think that any of your questions have been marked incorrectly, just please either send to my email address or open a private post on Piazza. Either way, I'll be able to see it. Okay. Any questions or concerns? Okay, so if there are no questions in today's tutorial, we'll be mostly going through the midterm questions and covering basic register allocator, covering a basic register allocator. So hopefully everyone has copied this down and okay, so because for the midterm, like most of the questions actually come with 2 versions. So I'm also not sure exactly which exact versions that you got. But those 2 versions, they basically share the same idea, like it's basically a parameter change in between those 2 versions. So yeah, let's start with the first question. I think the first question is done pretty well, which asks you, so what should be a proper type specifier for either the user or the operand? So the type specifier in both cases, the only valid one is a pointer to value. I think most people got this right. So the second question basically tests on your knowledge on Task Manager. So specifically, you were asked, so what happens if you run the command? As we can see from the past implementations, both B and C requires A. And it depends on whether B preserves A or not. If B preserves A, then the results you get is A, B, C. Or else the result you will get is A, B, A, C. Not preserved. And in the third question, the default behavior of the getAnalyzeUsage method, as we have described in class, is to require and preserve nothing. Preserve. The reason why it shall preserve nothing, why this shall be the default behavior, is because, as we have described, is because compiler design has to be conservative. Yeah, the average is 65. Not sure what other information you need. So, sorry, yeah, as I said, because those questions, they all come they all came with two versions. I assume that it's the ones that you got with user traversing through the user. I assume, is it correct? Sorry, traversing through from the user beginning up until to the user end. Well, you can try to see what this happens. You can go back home and try what happens as you try to cast those. But I remember I did. But I remember I removed the use option. I removed the use option in the user version because I saw that so it's too confusing. Yeah. So yeah, to answer your question, yeah, previously we announced that again. So the midterm average is average is 65, and we have assignment 2 due tonight, and assignment 3 will be released the next Monday. It will be on loop invariant code motion and register allocation. Okay, 3. LICM and rank alloc. And we'll be discussing, hopefully we'll have time today to discuss about register allocation today. Any other questions? Any questions about this? Would be up until to question 3. Any questions? No? So for question 4, the question you got is either ask you how to implement function info or how to implement multi-instruction optimization. I think in both cases, the question is done pretty well. Yeah, in the function info, the idea is that so again we get the uses, and for each uses we cast it into call instructions. And in the case of multi-instruction optimization, is that so for the instruction where query is uses, check whether it's the reverse operand or not. By reverse operand, we are only checking for plus, minus, multiply. We are not checking for division. So we are not checking for this case. The reason is because, so as an example, 1 divided by 2 multiplied by 2 is not equal to 1. So for question 5, it's either ask you to show a solution that is depending on which version you got. You either get a question that asks you to show an example why fixed point is smaller or equal to the maximum fixed point, or the maximum fixed point is smaller or equal to the mid or path solution. In the first case, a very easy way of showing it is to show similar to the example that we show why available expressions needs to have the universal set as the initial condition. That is, so we have something like this: a plus b as available, and it goes through this loop that keeps looping. If we assume that the initial condition is the empty set, we will still see that after converging, it still satisfies all the in and out equations that we have, but a plus b is no longer available in this basic block if we assume that the initial condition is the empty set. Whereas for the maximum fixed point is smaller or equal to the mid or pass, as we have described previously. So a simple example could be the constant propagation. I believe most of the problems in this case is that some people forgot what those solution stands for, and another issue is that they didn't demonstrate the smaller than relationship. Yeah, smaller than or equal relationship. Anyone has any questions about question 4 and 5 or any other previous questions that we have discussed? So if there are no questions, let's move on. For question 5, ask you to give a definition for question 6. For question 6, I ask you to give a definition for SSA, which is an IR where a variable is assigned at most once. Okay, and so yeah, the keyword is assigned at most once. So why does LVM adopts the SSA format? The reason is because it's more easy to track the definition use relationship and simplifies lots of optimization. Yes, we are doing midterm review. Yeah, we also have register allocation today after the midterm review. For question 7, for the final insertion process, we ask you why the dominance frontier is used in the case of final insertion process. The reason is because, so recall that the definition of dominance frontier says that it has to dominate its predecessor. Let's take this one, Y, as the dominance frontier, and we have this basic block X. The reason why it has to dominate some of the predecessors of Y is because the definitions inside X can propagate up until the predecessor of Y here. And the reason why it cannot strictly dominate Y is because we require that there are also some other program passes that flow through Y, so that there will be some merging of definitions going on here. And this is why we need to insert the final here to merge those definitions. So again, so the first half of the definition of dominance frontier, why it needs to dominate the predecessor is for the definition to propagate through. And the other is because so there needs to be some other program passes so that we'll be seeing this merging behavior. Any questions? So question 8 and question 9 both comes from your lecture slides. The dominance frontier for BB5 is BB7 or BB6. The dominance frontier for BB6 is also BB7. The reason is because 5 dominates itself, which is the predecessor of 7. And at the same time, 5 does not strictly dominate 7. And the places that we need to insert finals for J and K is, so we first insert at BB7 because due to the fact that BB5 and 6 both have definitions of J and K. And because we insert a final at BB7, consider the case of BB2. Because we have definitions from BB7 and BB2, so, sorry, BB1. So this is why we also need to insert a final at BB7 as BB2 as well. I think most people got this right. Any questions before we move on? Questions, concerns? Question 10 asks you to summarize what is lazy code motion, as we keep emphasizing during our tutorials. Lazy code motion consists of 2 parts. The first part is partial redundancy elimination. Partial redundancy elimination, and the second part is with minimum register usage. Or, I mean, shortest register lifetime. Some people just mentioned the first half of the partial redundancy elimination. This only explains up until to the earliest placement, but this doesn't really explain why we need the postponable expressions as well. So this is why we need 2 parts, which is the first part is partial redundancy elimination, and the second part is minimum register lifetime. Okay. Question 11 says, why an expression shall not be inserted at a place where it is not anticipated. So hopefully everyone still remembers the example that we have shown in class where we have let's say there's an expression a plus b here. Why we cannot put this a plus b to here? The primary reason is because this brings in this extra redundancy along this program passes, which previously does not have to evaluate the expression a plus b. So the first issue is redundancy, X redundancy, or performance. I think some students also mentioned this issue of like potential program crashes in the case of A divided by B, but that is not the primary reason, right? Because even if, as we have explained, even if it is not A divided by B, this can still potentially be an issue, as an example for A plus B due to redundancy. So I'm not right. Another issue is potential crashes, unexpected behavior. Yeah, where this one is the primary reason and it's more general. Question 12 asks you why we would like to derive the latest placement out of the earliest. And the reason is because, so as we have described, so earliest placement only removes the partial redundancy, does not consider register lifetime issue. And this is why we want the latest placement to postpone it before its uses, postpone E places until uses. Any questions here about lazy code motion? Questions here? No questions? For question 13, which is on control flow graph, I think most people handle this question pretty well. I don't think there's much issue with this question. Yeah, the only thing to pay attention to is perhaps between, I think some students mess up with unconditional go to versus conditional one if. Okay, so in this case, you directly jump to the specified label, whereas in this case, if this condition is evaluated to false, you will be going to the next instruction or next statement. or else you'll be going to the L1, which is the label L1 here. So each sub-question of this question is worth 2 marks. Yeah, we have 5 sub-questions here: basic block, CFG, dominator tree, back edges, and basic natural loops. So each is worth 2 marks here. Any questions here? So what about question 14? The first question of question 14 asks us, what is the basic induction variable? I think most students handle this correctly. So the basic induction variable here, in this case, is J. I is not the basic induction variable because at each iteration, I multiply itself, right? So here, hence I is not a linear increase. And based on whatever you get, you might get, like the parameters might be different, but you have K and N expressed as a linear combination of J. So the parameters might be different. But either way, like regardless of the version you got, there are 3 family of induction variables here, K and N. Those expressed as a linear function regarding J, the basic induction variable. As we can see in the baseline, the optimized code, the calculation for K and M requires a multiplication, which is expensive, right? Baseline. Multiply. However, we observed that because at each iteration we have J is equals to J plus 2, therefore we have K, we can transform this code into K prime is equals to K prime plus 6. And similarly, here we have whereas the 6 is basically 2 times 3. 2 times 3. And prime is equals to prime minus 8. And because n is calculated using m in the baseline, so you can directly write it and still preserve it as n prime is equals to n prime plus 7. Or alternatively, what you could do is that so you could write n prime is equals to n prime minus 8, but you might need some initializations in that case. We observe that after this transformation, the previously we have multiplication is simplified to adding or division, which is cheaper in comparison with multiply. Hence the name optimal optimization, which is stress reduction. Any questions here? Question 15, which is available expressions. Most people handle the question on meet operator and initial conditions pretty well. However, when it comes to actually performing the available expressions, there are two major issues. One major issue is the meet operator. So I think the solutions of many people didn't really converge, because if you check the meet operator conditions, it violates the solutions violate the meet operator condition. So that is the first problem. And the second problem is, so as we have discussed in assignment 1, as an example, we have this statement. Then in that case, I plus 2 is not available after the statement. The reason is because a re-evaluation of I plus 2 is not redundant here. So this is why I plus 2 shall not be deemed as available in this case. Any questions here? Oh, all right. So we finally got to question 16. So the problem of question 16 is actually pretty long, but if you read it carefully, you probably notice that. So the problem formulation of faint analysis is pretty similar to liveness that you are familiar with. The reason is because in both cases, they are dealing with dead code or unused variables, right? Unused variables. However, why is liveness unable to solve the problem that we specified in the problem statement? Let us just take the example in the problem statement where we have B is equal to A minus 3 and C is equals to A plus B here. As we can see, the issue with liveness is that liveness within variable B as live starting from this program point up until to this program point, right? So this is question 1, this is question 2. Yeah. And another thing is that I forgot to mention is for question 14, the marking scheme is as so you get the basic induction variable, right? It is 2 marks. You have the family of induction variables is 3 marks. If you have the transformed code, it is 12 marks. And finally, if you answer the explain why it has better performance, is 3 marks. This sum up to be 20. And in the case of 15, if you answer the meet operator, it is 2 marks. If you answer the initial conditions, it's 4 marks. And finally, for the analyzed results, we have 14 marks. And in the case when the meet operator or the special case that we mentioned is violated, there's a 2-mark deduction each. Yeah, and finally, in this case, for question 16, if you answer the related data flow analysis right, it is 2 marks. If you answer the defects of the liveness, is 4 marks. And if you answer correctly how to transform it, is another 4 marks. Okay, so back to here. So because B is live, right? So in the case of liveness, we won't eliminate B because B is live. So how should we solve the problem in this case? Well, the reason why B is live is because so in the transfer function, the reason why we set B as live in this case is because so we see that so B is used in this case, but we didn't really consider whether its left-hand side of the assignment is used as well, right? So this is why we have to improve this transfer function. I think some people mentioned the meet operator. However, that is incorrect. The reason is because if you check the examples that we have in the problem statement, the example in the problem statement that you have to do the meet operator, right? Because that's a single basic block. So therefore, what we have to do is so we need to improve the transfer function. So how should we do that? Well, the idea is so you change this transfer function to conditional. Right? In the sense that you should only be doing this transformation in the case when you observe that the left-hand side of the assignment C already belongs to your input. The left-hand side is either empty or the left-hand side of the assignment belongs to your input X. Or else you just preserve otherwise, input X otherwise. I think some people mentioned this case where they spotted the case why so in the case of, let's say, return statement or print statement, in those cases, so this actually corresponds to the case when we have the left-hand side as the empty set, Right. So in those cases, we transform the left-hand side as usual. The reason is because in those cases, let's suppose that we have something like a return C in the end. If we have a return C in the end, then all of this should be marked as live as usual, right? The reason is because as we do the transfer function here, we have the left-hand side, which is C, belongs to the input X, because at the return statement C, we already marked C as live starting from here. Because at this statement, the left-hand side is the empty set. Right. So for this question, so long as you have this sort of conditional thinking, I think you got full marks on this question. Yeah. Also, I think some students also answered doing this recursively. Well, that sort of got the idea, but it's just it's just a little bit vague in that case. Any questions here? About any questions that we talk about, or the midterm in general? Again, so if you have any problems with the midterm marking, either send me an email or open a private post on Piazza. Okay, so my email is okay. So if there are no questions, we'll be going to our next section, which is register allocation. Okay, and this will be part of your assignment 3. So in today's tutorial, we'll be covering a basic register allocation allocator, which we call as reg_alloc minimum. So the example code, as always, has been uploaded to GitHub. You can also open the GitHub page at this time, so that hopefully it makes it simpler as we describe the implementation of RA minimum. So if you check the implementation of the minimum register allocator that we have, it inherits from the machine function path. So what is a machine function? Well, to put it simple, a machine function is basically the same idea with the functions that we have in the IR, except that so it no longer has the finals. Function, but no finals. And similarly to function, A machine function has a list of machine basic blocks. And similarly to basic block, a machine basic block has a list of machine instructions. And our register allocator will be inheriting from the machine function path, where we have to implement this method run on machine function. As you can see, this is very similar to what we have previously when we do a function path, run on machine function. And the parameter in this case is a simple machine function MF. Machine function MF. Does anyone have any questions so far about machine function? I think, hopefully this is a relatively simple concept. All right, so if there are no questions, then let us go through again. So it might be better if you can open, because I need to write on the black whiteboard, so it might be better if you can open the GitHub pages at the same time so that you can refer to the code as we talk. Okay. Okay, so let us go through a simple example here. So consider the example that we have similar to what we had in class, where we have A is equals to something. If A is the case, if A is set to true, we have B is equals to something. Something is equals to A, and we have D is equals to B. And in the other branch, what we have is C is equals to something, something is equals to A, and again, D is equals to B. A is, as we merge this, we have A is equals to something, something is equals to A, something is equals to B, or return B. So this is pretty similar example to the ones that we had during lectures. All right. In the case of machine function, again, so we will be no longer having any finals in this case. However, for machine function, you will notice that so each instruction of the machine function has been assigned to a unique identifier denoted as slot indices. Slot index. So this actually belongs to the slot indices path. The slot indices path assign a unique ID to every machine instruction that we have. Okay. As an example here, so if you check the generated, machine function, print a generated machine function at the beginning of the run on machine function path, like we did in the example, you will notice that the basic block here, the starting slot indices is assigned from 0 up until to 128. The slot indices here has been assigned to 144 up until to 336. And the slot indices here has been assigned to 352 up until to 512. And finally, the slot indices in the end has been assigned from 544 up until to 800. So you might be asking, so why do we need those slot indices? The reason is because, so hopefully you still remember from your register allocation lecture, that in the case of register allocation, a very important thing is that so we need to know the live interval for every definition that we have, right? So the live interval is defined as the region where the definition becomes live up until when the definition becomes dead. Okay. So could anyone please tell me in this case, what is the live interval of, let's say, variable A? Anyone? What is the live interval here?
So it should be after the entire if branch, after going out the if branch. I think it's like, I mean like after the if else branch. That's nearly the end of this called resigned A.
Oh, here you mean?
Yeah.
Yes, that's right. Exactly. So as your colleague answered, the live interval of A is here and here. And oh, sorry, I did something wrong in this case. I think this should be D is using step. And similarly, the live range for B is here, and the live range for C is here. And for the live range of A and D, we have, for the live range of A, we have here. So this is another definition for A, right? And for the live range of D, hopefully everyone still remember how we merge the live ranges, which is essentially the same as the function, a phi function. We have those two definitions merged together here. So those are the live ranges. So in our so the first pass is the slot indices. In our get analyze usage method implemented in the minimal register allocator, you probably notice that so we have requested several other passes as well. So the important ones of them are first, the second thing that we requested is what we call virtual register mapping. Let me temporarily. Would everyone be able to see it if I write here, virtual register mapping? So from the virtual register mapping, we'll be getting, I think we are already running out of time. So I think let me preserve this material to next week because yeah, we are going to talk about assignment 3 annually next week. So yeah, so let me just stop here up until to the slot indices and the live intervals, and we'll be continuing our discussion next week. So again, thanks everyone for coming. If you have any questions about your midterm or assignment 2, please feel free to stay. Yeah, otherwise you're good to leave. Thanks everyone.